Welcome, guys. So, in this video, I want to introduce an interesting thing called a PDQP. Okay, so this is seldom people know about this, and this is introduced by the famous professor Scott Erickson. I think it's the 2014, and they define a new new complexity class called a PDQP. But seldom quantum mechanics people or seldom quantum computing people notice about this. But I mean, from the mathematical point of view, this PDQP is really interesting. So it can solve many problems in a non-usual way. So in this video, I introduced two implications if somebody can use this unnatural PDQP. So that means so one can just easily see that PDQP is somehow like generalization of the PQP, so it should be better than PDQP. So one can PQP. So one can try to use PDQP to examine the power of the quantum computing. So let's see the definition. So the usual quantum mechanics is that if somebody give you alpha XX, which is the resulting state, then if you measure, you will get the eigenstates, right? If you measure in a computational basis, you get X, and with the probability alpha X squared. So this is the standard quantum mechanics. So one can view this rule define PQP, right? So this is the idea in the usual quantum computer that the problem for the computer is that if once you measure it, then most of information got lost. Okay, so what about if somebody can get this? So what is the definition of PDQP? The PDQP is that there's a thing called there's an unnatural thing called non-collapsing measurement. So non-collapsing, measurement. Okay, so hopefully my spelling is not definitely not correct. So there is a thing called non-collapsing. What hell? Do not collapse, right? So so my spelling should be correct. Okay, yeah, so non-collapsing measurement. So that means that if you have a resulting state, let's say alpha XX, then once you measure the resulting state still be alpha XX, but you get X, but you will get X, right? Yes, the same with prob alpha X squared. So the idea is that the state will not collapse, right? So the PDQP contains two measurements. One is the so-called usual quantum mechanics usual measurement, and this is the much powerful measurement called non-collapsing. So PDQP contains two kind of measurement, and we assume that PDQP can perform each measurement independently or however they want. When they want to use the usual quantum mechanics measurement, they can do it. When they want to use the non-collapsing measurement, they can do it. Okay, so let's assume that we now have the superpower for a new kind of quantum computer called PDQP, and we can solve all the problems. Okay, so let's take Scott Erickson's two example. From my point of view, I think it's very interesting if you just think this is a pure mathematical object. Okay, so the first thing is that the very famous collapsing problem, right? So collapsing, or basically it's a collision problem. Okay, so collision problem is that if you have f from 0, 1, 1, 2, 2, 2, 2, and minus 1 map to 0, 1, 2 to a minus 1, and the idea is that we already assume that f is 2 to 1, right? So basically, there are always two f mapped to the same thing, right? So the classic collision problem is that find x, y, right, such that x is not the same as y, and f of x equals to f of y. Okay, so this is the standard problem. So if you use as we already proved before, if you use classical, then you need like the order n, right? Because you need to first measure from 0 to minus 1. You need to first measure 0, 1, and 2 up to n divided by 2 plus 1. And then you make a record, and then you starting to see the rest, and you can easily find such one. So classically, you approximate the n, and then we prove that in the BQP, right, you can use a Grover's algorithm. So you first choose one over third, and make a dictionary, and use Grover's, right? Use the Grover's algorithm to square root of the rest. Okay, so both are just approximated O and 1/3. Okay. How about this super powerful unnatural thing called PDQP? So let's say PDQP. So for the PDQP is powerful that okay. So basically, if you're starting from the Hadamard gates, right? So the standard quantum mechanics, quantum computing is that you first create everything in the superposition, and then you apply the oracle f, right? And then you will get this x f of x, and x0 and -1, right? Square root of n. So let's make so first, if we have PDQP, let's first make a usual measurement, right? So usual measurement, right? So once we use the usual measurement, then we will get some f of x, right? But we already see f is 2 to 1. So if I measure in the second basis, then I will get the 1 over square root 2 for some x plus y, and this is f of x, and they satisfy the f of x equals to f of y by definition. Okay, then second step is that we perform the magical non-collapsing measurement. So non-collapsing, I use NCM. Okay, so non-collapsing measurement. So since it's non-collapsing, right? So I have a prob of 2 to get the a probability of half to get the x, and I get the probability of half to get y. But after I measure it, the resulting states is still the same. So you can view there's a ball, there's a box, and you have the prob of half to get a red ball, and you have a prob of the half to get another color ball, right? But the situation is always the same. So expectation value for give the correct answer is just 2. So the expectation value of the Curie, the number of Curies is just 2. Right, so which is super powerful, right? Super powerful. So for the classical, you need n. For the BQP, you need n to the 1/3, 1/3, right? And the BQP, you only need 2. You only need 2. Right. The idea is that because the usual measurement, because after usual measurement, this step will not collapsing. So if you try to use the classical if you try to use the original BQP, then once you use the BQP, then this step will disappear. So you will lose this step. Once you use the standard BQP, once you use the collapsing measurement, so the standard BQP. So the only way that we can solve is we assume that there's a unnatural superpower for non-collapsing measurement. Okay. Okay, so that's the second. So the second is Grover's. Okay, so Grover's algorithm. So this is what I think is really also terrible, but interesting, right? So let's say, so Grover's algorithm means that let's assume that you have f1, 0, 1, 2, -1, like up to like 0, 1, right? And only one x, such that f of x is 1. The rest, f of x is 0. So this is like the black box problem. You have a box, right? But there's only one correct element, one correct answer. Okay. So the classically, there you have no way. You can only take a root n, right? But if for the famous Grover's algorithm BQP, if you don't know about this, then you can go to my other video to see the rigorous proof of why BQP need a half, right? So it's n to a square root of n. Okay, so how about the BDQP? The PDQP. Okay. Okay, so this is also amazing. Okay, the amazing is that let's say PDQP. Okay, so amazing is that The idea is that your original states, if you try to using our original way, right? This is our original states. If you get this, then your problem is that you will get the you will get the correct x but 1, right? And the rest of the many states. So you get maybe y and 0 for all y there. So it's -1, but y is not the same x. So if you do a normalization, this is still 1. This guy, right? This is somehow right, this guy, right? So in the usual Grover's algorithm, we perform the amplitude amplifier, right? So the usual Grover's, tell you what? Grover's tell you that after t step, the prob of x will be t squared divided by n. So that's why in Grover you need a square root of n, because you want these to be all 1. So t need to take a square root of n, right? But now we can first do n to the 1/3 Grovers. Okay, so once I do n to the 1/3 Grovers, the prob of x, the prob of getting x will be n to the 1/3 squared divided by n. So it's still 1 over n to the 1/3, right? It's correct. So the prob of you getting x is 1 over n to the 1/3. Then we perform. So we can perform the non-collapsing measurement. So non-collapsing measurement on the resulting states. Okay. So the expectation value for we to get the correct x is 1/3, n to the 1/3, just the inverse of this one. So total we need n to the 1/3. Okay, so this is much powerful than the Grovers. So that's summary for the black box. If you use classical, you need n. If you use the standard PQP, you need n to the square root of 2. If you use the much powerful that called the product dynamic quantum polynomial time, you need n to the 1/3. So PDQP is much powerful than BQP and all classical, right? Although nobody knows why they are. Nobody can strictly prove that they are actually much powerful than it. So this is the I should say P or P. Okay. Although classically, yeah, indeed need P. Okay, so that's it. So that's why I think this called product dynamic quantum polynomial time are interesting. So if you are interested more, then you can go to see other video. You can go to see the rest of these papers. So I just want to introduce this paper a little bit by just showing you guys this collection problem, and the Grover's algorithm can be enhanced by this PDQP. So amazingly is that if you allow the quantum computer can perform so-called non-collapsing measurement, then you can solve more problems. But the problem is that even though you enhance the quantum computer by allowing use the non-collapsing measurement, then it seems like that in their paper, it seems that you still cannot solve the NP complete problem. So that means it provides some evidence that the BQP, the quantum computer, cannot solve the general NP complete problem, even though you try to enhance them. Okay, I will see you guys in the next quantum computing video channel list. So be sure to subscribe to my channel. I will see you guys in the next videos.